Video, we're going to talk about the focus-directrix property of conics. So there's some notation here that I'm going to introduce you to. This upside down A means for all. And this backwards E means there exists. So this sentence says, for all conics, there exists a focus and a directrix. Okay, so far we've only talked about the directrix in terms of the parabola, but all conic sections actually do have a directrix. We're going to define D2, so this triple equal sign just means is defined as. So D2 is going to be defined as the distance from some point on the conic to the focus, and D1 is defined as the distance from the point on the conic to the directrix. Okay, and now for a parabola, we said the distance from all points on the conic to the focus is the same as the distance to the directrix. But for other conic sections, that's not true. You got a secret sneak preview of the focus-directrix property just for parabolas. For all conic sections, the property is this, that D2 is going to be proportional to D1. But it's related by a proportionality constant that we call E, which is the eccentricity. So this is not special E 2.718. This is E is defined as the eccentricity. So we might not, so for a parabola, we know that D2 is equal to D1, which means that E is exactly equal to 1. So if I have some given conic section, I have a parabola, then I can calculate what the eccentricity is. And for a parabola, no matter what parabola it is, the eccentricity is always going to be equal to 1. For hyperbolas and ellipses, however, the eccentricity will vary depending on how narrow each of the shapes are. So if an ellipse is super stretched out, its eccentricity is going to be different than if the eccentricity is very close to a circle. Generally, if the eccentricity is super small, so you're like 0.01, then it's going to be a more circular ellipse. And if it's much larger, then you're going to end up with a more rectangular or stretched out ellipse. But given some conics, the eccentricity is fixed so that every single point on that conic, so if I have a hyperbola, every point on the hyperbola has the same proportionality of distance from the directrix as it does to the focus. Okay, so what we're going to do is try to prove that this is true. Okay, so we're going to say that xy is some point on the conic, and we're going to put our directrix is going to be at this will be some vertical line x equals k. Okay. And what I'm going to do is I'm going to plug this into the focus-directrix property. And if this works, I should end up getting an equation that looks like a conic equation. Okay. So in order for me to do this, I'm going to say D2 equals ED1. And now I need to calculate the distance from this point, xy, to the focus. Okay. So our focus here, we're going to put at 0, 0 for convenience. Okay, we'll just choose focus at 0, 0 because that is the easiest thing to do. Okay, so from here, we're going to say, okay, well, the distance, I can just do with the distance formula. This is going to be the square root of x squared plus y squared is equal to E times whatever the distance is from my point to my line, my directrix. So that point, since this is a vertical line, I'm just interested in how far apart the point, the x coordinate of my point is from the line, right? So that is going to be equal to x minus k. And I'm going to do absolute value of x minus k, because if k is negative, then I need to make sure that I'm adding, right? To just briefly diagram this, because this is something that people get confused about sometimes. If I have my point xy, and then I have my coordinate plane. So if I have this, if this is k, x equals k, then my distance here is just x minus k, right? And that is how far apart these two things are. But if I have something over here where x is negative k, then I'm going to have x and then plus this k. So x minus negative k does in fact give me plus, so that works out. Okay. So that's why we're doing absolute value, to make sure we get a thing that makes sense. So in order to solve this, I'm going to square both sides. So I'm going to get x squared plus y squared is equal to e squared. And then once I square this, anything squared is positive, so I can get rid of the absolute value bars. So I have x minus k squared. And now I'm going to distribute out this side. So I'm going to have x squared plus y squared is equal to e squared x squared minus, I'm going to have 2 kx times e squared. So 2 e squared kx, then plus e squared k squared. Okay. And now I'm going to do some rearranging here. So this is going to become x squared minus e squared x squared. I'm just going to put everything on the left side, plus y squared plus 2 e squared kx minus e squared k squared equals 0. And now I'm going to sort these and basically just factor this part out because everything else is already set up. So this becomes 1 minus e squared x squared plus y squared plus 2 e squared kx minus e squared k squared equals 0. Okay, so this equation, you'll note firstly, it's missing a y term. The reason it's missing a y term is because we chose our directrix to be vertical, and therefore we did x minus k. If we had a horizontal directrix, then it would be y minus k, and we'd have a y term and not an x term. Regardless, remember that the general form of a conic equation is ax squared plus bxy plus cy squared plus dx plus ey plus f. And this satisfies that, right? We have a x squared term and a y squared term, and then we have some other stuff going on. But as long as we have the two quadratic terms, that's going to give us our conic. And the interesting thing here is this 1 minus e squared in front of the x squared, because this is actually going to control which conic section we get. Okay, so let's look at why that happens. I'm going to try to keep that equation up. E squared, k squared. Okay, so let's look at what happens if we vary e around 1. If e is greater than 1, then what happens? Well, x squared and y squared have opposite signs. Opposite signs. And we know which conic has opposite signs on x squared and y squared. A hyperbola does. So if the eccentricity is bigger than 1, you're going to end up getting a hyperbola. If e is equal to 1, we actually already said this out front, right? If e is equal to 1, then this x squared term vanishes because 1 minus 1 is 0. So if it vanishes, that means we have only one quadratic term. Which means we have a parabola. And then if e is less than 1, then x squared and y squared have the same sign. And if they have the same sign, we have an ellipse. So this is a quick and easy way to determine which kind of conic section you have. By looking at the eccentricity of the conic, you're able to determine whether you have a hyperbola, a parabola, or an ellipse. A circle is sometimes said to have eccentricity 0, but we can't actually use a circle with the focus-directrix property of conics, because as you take e to 0, if you look at this equation, everything kind of blows up and it degenerates to a point, because this term becomes 0, this term becomes just x squared plus y squared, and then we have this term is 0, so I have x squared plus y squared equals 0, which gives me a point instead of a circle. So in order to actually get a circle, you'd have to have the directrix infinitely far away. Okay, so really the focus-directrix property of conics is for hyperbolas, parabolas, and ellipses. So now we're going to look at how to actually use this to solve things. Make sure you have down especially this kind of key for eccentricity relating to conics, because that's going to be important going forward. So let's look at a problem. Let's say I want to find the equation of a conic that has a focus at 0, 0, so a focus at the origin. It has a directrix at, we'll say, y equals 2. And it has an eccentricity of 3. And I want to find the equation of this conic. So the way we always start, if you have stuff with eccentricity and focus and directrix is we're going to use the focus directrix property, which says that the distance to the focus, which is d2, is equal to e, eccentricity, times the distance to the directrix, d1. Right away, I see that e is equal to 3, so I know that because this is bigger than 1, I should end up with a hyperbola. So it's a good check on my final answer. I should end up with an equation that looks like a hyperbolic equation. The x squared and the y squared terms should have opposite signs. So I'm going to plug everything in here. So since my focus is at 0, 0, we have a nice and easy distance from an arbitrary point xy to the focus. You always plug in an arbitrary point xy because you want to generate the set of all arbitrary points xy that satisfy these conditions. And that will give you the conic. So here we're going to have the square root of x squared plus y squared is equal to 3 times the absolute value of the distance between our arbitrary point xy and the directrix y equals 2. You'll note that this time our directrix is a horizontal line instead of a vertical line. So that means that I'm interested, if I want the distance from the point to the line, I'm interested in the vertical distance, right? So that means that I'm going to do y minus 2. Okay. Quick and easy way to remember is whatever the directrix is, if it's y equals 2, you're going to have y minus 2. And if it's x equals 2, it's going to be x minus 2. Okay. And now we're going to square both sides. So I'm going to get x squared plus y squared equals 9 times, I'm going to square all this, so I'm going to get y squared minus 4y plus 4. I can distribute the 9, I can put everything on the same side. When I do some algebra here, I should end up getting x squared minus 8y squared plus 36y is equal to 36. So now we're in the spot where we started in the past before we had the focus-directrix property. So the focus-directrix property gets us to this general equation where now I'm going to have to complete the square. I'm going to warn you that when you're doing focus-directrix, completing the square will not always give you nice numbers. It used to when we were kind of warming up and given nice equations to start with, but given arbitrary foci and directrices, the numbers are not going to work out. So this is going to be x squared minus 8 y squared plus, and you can already see that this doesn't really work out here, right? So I'm going to have y squared, I think 4.5 is going to give us what we want. So I have to actually factor the negative 8, so that means that that plus sign should be a minus. So we're going to have y squared minus 4.5 times y. And then if I want to complete the square, I take half of 4.5 and square it. And that's going to give me 5.0625. And then I have to do 36 minus 8 times 5.0625, or plus negative 8 times 5.0625. 8 times 5.0625 is 40.5. So 36 minus 40.5. So then I can, rewrite this nicely, or nicer. I have x squared minus 8 times y minus 2.25, which is half of 4.5, squared, is equal to negative 4.5, which I'm going to write as negative 9/2. For this problem, I'm going to keep everything in fractions and show you how you could do it if you keep things in fractions. It's kind of a pain to do because you have so many gross numbers that it's often easier to just work in decimals. But I just want to show you that it can be done if you so desire. So this one I'm going to do in fractions. The next one I'm going to stick with decimals. So I'm going to convert this back to a fraction in a second as well. Or we'll keep this. This is going to be what, 5 or 9 over 4, right? 9 over 4. So this is going to give me, as I do this, we're going to divide everything by negative 9/2. So that means that the y term is going to end up being positive, and the x term is going to end up being negative. So if I do that, I'm going to get 16 y minus 9/4 squared divided by 9 minus 2x squared over 9 equals 1. So this is pretty close to a hyperbola equation. The only real thing we're kind of missing here is, it's nice to have everything in the denominator. So what I'm going to write this as is I can rewrite this if I want. You can keep it like this. That's fine. Just keep in mind that a here is not 3, right? A is going to be equal to 3/4, right? Because you have 9 over 16. And that's why I'm going to put this in the denominator. You can see why keeping it in fractions is kind of a mess, and it's preferable, I think, a lot of the time to keep it as a decimal instead when the numbers are not nice, because this would come out to be 9/16 and then minus x squared over 9/2 is equal to 1. So this would mean that a would be equal to 3/4, b would be equal to 3√2 over 2. And this is all well and good, but when you want to go graph it, like 3√2 over 2 is not a trivial thing to just plot on an axis. So then I'm going to convert to decimals anyways, right? So we have 0.75, and that'll be easy to graph, and then 2.12 approximately. So that'll be nice to graph. And you'll get a hyperbola. You'll just graph it like normal. I'm not going to really go through it, but your vertex will be up here, and you'll do your little box around it, and then you'll graph your hyperbola, and it should be like this, okay? Because your y term is positive, so your transverse axis is vertical. So this is certainly involved, and it's going to take some practice. And it gets even more complex when your focus is not at the origin. And that's the kind of problem we're going to look at next, because that's something that you need to know how to do. So now we're going to say that instead we have a focus at -1, 2, a directrix at x equals 3, and an eccentricity, which is equal to 3/4. So I see that this is less than 1, and right away I say, okay, this should be an ellipse. So when I get to the end, a good check on my answer is going to be whether x squared and y squared have the same sign, because they should. They should both be positive. We have an ellipse. So I'm going to go ahead and say that the distance to the focus has to be equal to eccentricity times the distance to the directrix. The distance to the focus here is not just going to be square root of x squared plus y squared, because I have to do the distance formula with another point that's not 0, 0. So the distance to the focus here is actually going to be x minus -1, so x plus 1 squared, plus y minus 2 squared. And that's going to be equal to my eccentricity, which is equal to 3/4, times the distance from my point xy to the directrix. Because this is x, I'm just do x minus 3. Right here I have a vertical line, so I'm interested in the distance horizontally to the line, to the directrix. From here, we have to square both sides of this equation. So this is going to give me x plus 1 squared plus y minus 2 squared is equal to, and on this side, we're going to end up getting 9/16. And I'm going to put this in decimals pretty soon once we have to start completing the square. Before we complete the square, I'm going to keep it in fractions because stuff still works out nicely. But the moment we have to start having stuff and squaring it, we're going to switch over to decimals, like I said. So we have 9/16 times x squared minus 54 over 16x plus 81 over 16 as a constant. So I'm going to multiply everything by 16 so I can get rid of 16 on this side, and then on this side I can distribute 16 to all of this stuff, which I am also going to FOIL out. So then I'm going to get 16 times x squared plus 2x plus 1 plus y squared minus 4y plus 4 is equal to 9x squared minus 54x plus 81. And I can factor out the 9 if I want to get something closer to this, but I'm not going to do that because I'm actually just going to distribute the 16 in so I can combine all my like terms. So here I'm going to get 16x squared plus 32x plus 16 plus 16y squared minus 64y plus 64 equals my stuff on the right, 9x squared minus 54x plus 81. Now we combine all the like terms. When you combine the like terms here, you should get 7x squared, because I'm doing 16 minus 9. And then we do 32x plus 54x is plus 86x. And then for my y term, all I have is 16y squared. So I'm going to do plus 16y squared. For 64y, I similarly don't have any other y terms on this side, so I still have minus 64y. And then I have 64 plus 16 is 80. 80 minus 81 is negative 1, and that's equal to 0. So this line is where now we have to complete the square. So we've finished kind of the focus-directrix part of the problem. We've generated an equation in general form, and now we need to complete the square to put it into standard form. So from here, I'm switching to decimals because the numbers are no longer going to be nice. So we're going to have 7 times x squared plus 12.29x plus 37.73. Where what I have done is I have factored 7 out of 86, and then I'm completing the square here. So I'm doing half of, whatever that is, which would be like 25-ish or something. And then we're going to take half and square it, and that gives us our constant here. And then we're going to do plus 16 times y squared minus 4y plus 4. And that's going to be equal to 1. And then we have to add in the stuff that we have on the other side. So 7 times 37.73 is plus 264.14, and then plus 64. Okay. Good. So again, 7 pulled out of 86 is 12.29, and then you take half of 12.29, which is, a little more than 6, square it, you get a little more than 36, 37.73. Do the same thing over here. This one's nicer. 16 pulled out of 64 is negative 4. Halve it and square it, you get positive 4. And then we have to add everything to the other side. And then you get to just write this as 7 times x plus 6.14 squared plus 16 times y minus 2 squared equals 329.14. Now we're going to divide everything by 329.14. When I do that, I'm going to write this. You'll see how I write this in a sec. So this is going to be x plus 6.14 all divided by 6.86 squared. Okay, so what I did is I divided on the left side. I did 7 divided by 329.14. I took the square root of that and squared it. So the whole thing is squared, because this way I can just look at this equation here and say, oh, this is just going to be, the a is going to be equal to 6.86. And I don't have to take an ugly number and square it. It's just a nice way to write it. You don't have to. If you'd like, you can say, okay, well, 7 over 329.14 is some incredibly small number. Invert that, right, because you're dividing by it on the bottom, and you get this. So then we do the same thing over here. So we do plus, I'm going to write it as y minus 2 over 4.54 all squared is equal to 1. Where here I did 16 divided by 329 is a really small number. And we'd have that really small number times y minus 2 all squared, but I need something divided. So you invert it and you put it on the bottom, which means you could shortcut and just say, well, what's 329 divided by 16, and put that number on the bottom, and then square root it, and that's what goes inside of your overall squared. If we had kept it in the kind of form that we've been using, then you would see this as x plus 6.14 squared, all divided by 40-ish, because you're going to have something probably a little bigger than 40. And then over here you'd have y minus 2 squared, all divided by around 20-ish. Okay. And this is an ellipse as we predicted. The signs of the x squared and y squared terms match. So we are all set with the ellipse. So when you're doing these problems, be very careful. There's a lot of algebra. And the other thing to keep in mind is that just remember what D2 and D1 are. People mix them up a lot. D2 is the distance to the focus. D1 is the distance to the directrix. And as long as you get that, this kind of process of set these equal, use distance formula over here. Here you're taking the distance just between one of the coordinates and the directrix, square everything, and then solve, get it into the nice general form, combine all the like terms, and put it into standard form for graphing is kind of your overall process. And that's the focus directrix property for conics. Thanks for watching.